in addition to jumping between polar and Cartesian, you also might need to add vectors. So now let's think about accelerations just for fun rather than v's. So let's say we're looking for the sum of two accelerations. So a sum is a1 plus a2. So for whatever reason, a mass is experiencing two accelerations in different directions, and we want to know the total. Therefore, we just have to add them to get the total. How do we do it? Okay. Well, first, let's do it again in two separate coordinate systems. In polar coordinates, how would you do that? Polar coordinates, if you're given two magnitudes and two angles, how would you combine those in polar coordinates without going to Cartesian? Now this is where you do it what's called head to tail. So say we have A1. So I guess to do this, I need to get a little bit of a vector anatomy lesson going. The head is the arrowhead, right? That's where it's going. And the tail is the back. So it's pretty much, if you anthropomorphized a vector, pretty much what you would expect. So we'll say we have A1 like that, and say we have A2 like that. And we want to add them. So head to tail means, let's see, this one, both of their tails are here and their heads are here. Pretty much what it means is you draw A1 the same, and you move A2 to where we have head to tail. This one's head is at this one's tail, right? So then you move this one like there. Okay. You can often move vectors around in physics problems, right? So you might say, well, why can you move it? Isn't this the origin? Well, this is the origin in space. These are acceleration vectors. So you can actually move them around wherever is convenient, usually. If you're doing position vectors, then it gets more problematic. Anyway, there's A1, there's A2, head to tail. And then the final step is to draw the sum vector from the first tail to the second one's head. So there is a sum, like that. And you could say, what if I did 2, 1? You see, we'd get the same thing. We could have A2 and then move A1 head to tail, would get the same vector. And then you might say, well, that's great, but how do I get a number? And the answer is you'd have to do it graphically. Really, if you got on graph paper and drew your vectors and gave them the right magnitude and angle, you would graphically measure literally what a sum is. Okay? If you really want to do it mathematically, you need to go to Cartesian coordinates. So let's look at how we add vectors in Cartesian coordinates. Let's see, in this case, let's have the same, let's see, what you do is you simply add the components. So let's take the same two vectors. Here's A1, and here's A2, like that. And you break them into components. You say, okay, here is A1x, right? And here is A1y, and here is A2x. Looks like it goes just a little bit further the way I drew it. And here is A2y. I'm drawing the components as though they are vectors with dotted lines, and I'm not putting, and we're treating them as scalars, but it's really just, that's kind of how we're doing it. So just imagine them as the component. I'm just trying to help you visualize the component. I'm not trying to write them as more vectors, although we could. So then a sum, in this case, we could get it mathematically. It would be a1x plus a2x, I'm sorry. So a sum, if we wanted it in Cartesian coordinates, a sum, the x component, would be simply a1x plus a2x, and a sum, the y component, would be a1y plus a2y. And then if you wanted to go back to polar coordinates, you could. You would just have to do the square root of this squared plus this squared is the magnitude, and the angle is the inverse tangent of this over this. But really in Cartesian, we just need the 2 coordinates, and then we have the vector. So let's see if we think this looks like it's going to give the same thing, right? So let's look at the 2 a1x's. Let's see, a1x, a2x, the x component, it looks like it should be longer, right? Because these are both positive. When they go the same direction, or in this is the positive x direction, those are both positive x numbers. So it's going to get bigger. So it's going to have a big x component. And the graphical method, sure enough, did give us a big x component. Right? It's bigger than this one and bigger than that one. In the y direction, these 2 numbers, remember these are really scalars, these components. One is in positive and one is in negative. So when you add these, it would actually cancel. They're about the same size and they're opposite directions. So a2y would be a negative number. They'd pretty much cancel, give you pretty much nothing. And sure enough, the sum has essentially no y component. Right? It's pretty much flat because the y component's canceled. So the 2 really are giving about the same, well, they're giving exactly the same thing to within the precision of my drawing. Right? But anyway, that's how you add vectors. You can do it either way. Usually when you're getting a mathematical answer, you've got to break it into Cartesian components.